In this class, we will discuss the 5-number summary and the box plot. First, let's see what's percentile. For each p between 0 and 100, the p's percentile is the number that divides the bottom p% of the data from the top 100 minus p%. You should know this quantity. When you take the SAT test, the score report includes a percentile. For example, if your percentile is 85%, it means that your score is higher than 85% of people who take the SAT test. We use the letter P subscribed with the percent to denote a percentile. For example, P30 is the 30th percentile. Median is exactly the 50th percentile, or P50. Similarly to the median, percentiles are resistant. The most commonly used percentiles are quartiles. We have 3 quartiles. The first quartile is the 25th percentile, denoted by Q1. The second quartile is the median. We may denote it by Q2. The third quartile is the 75th percentile, denoted by Q3. The following 4 plots show the rough locations of the quartiles for different shapes of distributions. The 3 quartiles essentially divide the whole range of a dataset into 4 intervals. Each interval contains 25% of the data. For the uniform distribution, the 4 intervals roughly have the same length. In other situations, the intervals are shorter for the middle 50% of data, but are wider for the top 25% and the bottom 25% of the data. In order to determine the quartiles, we first need to arrange the data in increasing order. Next, determine the median. We will partition the ordered dataset into 2 halves according to the median. If the sample size is even, each half exactly contains the half of the original data. If the sample size is odd, we include the median in both halves. The first quartile, Q1, is the median of the bottom half of the data. The third quartile, Q3, is the median of the top half of the data. Notice that the rule of calculating quartiles is not unique. When reading a different book, you may have a different rule. However, when the sample size is large, the different rules should give you similar numbers. Let's look at an example. The data are weekly TV viewing times of a sample of 20 people. The data have already been sorted in increasing order. First, we need to find the median. Because the sample size is 20, it is an even number. The median is the average of the 2 middle numbers. Here, it is the average of 30 and 31. So the median is 30.5. All numbers smaller than 30.5 give us the bottom half of the data. All numbers larger than 30.5 give us the top half of the data. For the bottom half, the sample size is 10. Its median is the average of the 2 middle numbers, or the average of 21 and 25. It is 23. So the first quartile is 23. For the top half, the median is the average of 35 and 38. It is 36.5. So the third quartile is 36.5. As a summary, the 3 quartiles for the TV viewing time are Q1 equals 23 hours, Q2, or the median, is 30.5 hours, and the third quartile is 36.5 hours. Recall that the three quartiles divide the whole range of data into 4 intervals. Each contains 25% of the data. Therefore, 25% of the TV viewing times are less than 23 hours. 25% are between 23 hours and 30.5 hours. 25% are between 30.5 hours and 36.5 hours. The remaining 25% are larger than 36.5 hours. Let's look at another example. The data are maximum wind speed for 19 tropical cyclones in the Atlantic Basin in 1 year. The sample size 19 is an odd number, so the median is exactly the middle number in the ordered list. Here it is 80. Because the sample size is an odd number, when partitioning the data into two halves, we include 80 in both halves. Therefore, the bottom half contains 10 numbers, and the top half also contains 10 numbers. We can find medians for these two halves separately. The first quartile is therefore equal to 55, and the third quartile is 95. As a summary, the three quartiles of the maximum wind speeds are Q1 equals 55 miles per hour, Q2 or the median is 80 miles per hour, and Q3 is 95 miles per hour. Roughly 25% of the maximum wind speed are less than 55 miles per hour. Roughly 25% are between 55 miles per hour and 80 miles per hour. Roughly 25% are between 80 miles per hour and 95 miles per hour. And roughly 25% are larger than 95 miles per hour. Interquartile range is another measure of the variation of a dataset. It is defined to be the difference between the first quartile and the third quartile. We sometimes denote it by IQR. For example, for the data of weekly TV viewing times, we have already calculated that T1 is 23 and Q3 is 36.5 hours. Hence, the interquartile range is their difference, or 13.5 hours. The middle 50% of the TV viewing times are spread out in an interval of length 13.5 hours. The 5-number summary of a dataset is mean, Q1, Q2, Q3, and maximum. These 5 numbers partition the whole range into 4 intervals, each containing roughly 25% of the data. In the example of TV viewing times, we know that mean is 5, Q1 is 23, Q2 is 30.5, Q3 is 36.5, and the maximum is 66. Outliers are observations that fall well outside the overall pattern of the data. They are usually much larger or smaller than the remaining data. If there is an outlier, we need to check whether it is due to a recording error. For example, you may misplace the decimal point. You may also want to check whether it does not belong to the dataset. For example, you want to collect the height of some school kids, but you include the height of a teacher by accident. Another question is how large or how small an observation is to be classified as an outlier. Usually, an observation below the lower limit or above the upper limit are potential outliers. The lower limit is the first quartile Q1 minus 1.5 interquartile range, and the upper limit is the third quartile Q3 plus 1.5 interquartile range. For example, in the data of weekly TV viewing times, the first quartile is 23, and the interquartile range is 13.5. The lower limit is therefore 23 minus 1.5 times 13.5 equals 2.75. The minimum of the data is 5, which is larger than 2.75. Hence, no observation is smaller than the lower limit. Similarly, the third quartile is 36.5, and the interquartile range is 13.5. The upper limit is 36.5 plus 1.5 times 13.5 equals 56.75. There is one observation, 66, which is larger than 56.75. Therefore, there is only one potential outlier in this dataset. The 5-number summary can be presented in a plot called Boxplot. Sometimes it is also called a box and whisker diagram. The plot on the slide is the Boxplot for the data of weekly TV viewing times. There is a box in the middle. The line in the middle of the box indicates the location of the median. The two boundaries of the box indicate the values of the first quartile and the third quartile. The length of the box is the interquartile range. There are two arms on each side of the box. They indicate the location of adjacent values. For adjacent values, we mean the most extreme observations that still lie within the lower and upper limits. Any potential outliers or any observations smaller than the lower limit or larger than the upper limit are marked with asterisks. This slide explains the steps to construct a box plot. Firstly, we need to determine all values, including the quartiles and the potential outliers and the adjacent values. Then, we first draw lines at the location of Q1, Q2, Q3, and two adjacent values. At the end of this step, you will get the first plot in the bottom. Then, connect the quartiles to make a box. Connect the box to the adjacent values within lines. Now you should get the second plot in the bottom. In the last step, plot each potential outliers within an asterisk. Now we complete the box plot. Box plots can be used to quickly compare summary statistics of different datasets. In this example, a study was conducted to determine whether elite distance runners are actually thinner than some other people. Hence, we collect data from two different groups of people with similar age. One group includes runners, and the other group contains other non-runners. The researchers measure the skin fold thickness of them. The skin fold thickness is an indirect indicator of body fat. A smaller value indicates thinner. We draw one box plot for each group of people. We can see that the box plot for runner is much lower than that for others. All values, Q1, medium, and Q3 are smaller. It indicates that the skin fold thickness of runners are uniformly smaller than that of others. The width of the box is interquartile range. The width of the box for runners is much smaller than that of others, which indicates that the variation of the skin fold thickness is in runner is also smaller than that of others. In this slide, we place the box plot along with the distribution. It helps us understand how to read a box plot. When a distribution is symmetric, the line for the median is exactly in the center of the box. If the distribution is skewed, the line for the median will be closer to one end of the box. Additionally, if the distribution is skewed, one arm of the box plot will be much longer than the other arm. Therefore, by looking at a box plot, we will be able to know the skewness of the distribution. This table lists Excel functions to calculate quartiles. This function has two arguments. The first argument indicates the data range, and the second argument indicates which quartiles you want. 1 means the first quartile, and 3 means the third quartile. There is no Excel function can be used to calculate the interquartile range directly. We need to first calculate the first quartile and the third quartile separately, and then calculate their difference to get the interquartile range.